Today, I'm acting as a pale shadow of the hobby. I'm not tanned at all. We have a very interesting schedule this afternoon. And the first speaker will be, as you can no doubt figure out all by yourselves, Razieh Emami, who has been at the center now for almost 6 months, or maybe just 6 months. But she knows the place, she can find her way around and everything. It took me 6 months to learn how to navigate this whole place with walls. Anyway, so she will be the first speaker. The next speaker will be Fabrycky, who hasn't been here in almost a decade and is firmly ensconced in the University of Chicago, Chicago being, as I just learned, his hometown, and he's going to be discussing far-out exoplanets rather than the neighborhoods in Chicago. And the third speaker will be Amina Helmi from Groningen, who just gave us a fantastic talk on the DR2 release of Gaia and what one can deduce from it. The 7 million stars, they have all 6 characteristics of all 3 velocity and position components, and it's amazing what they've been able to deduce so far from these data. The Milky Way is far, far more complicated than anyone, well, I shouldn't say anyone, probably someone before it was complicated, but it is very complicated, and they're now elucidating a lot of this. And the fourth speaker will be Richard Anantua, who has been here now for all of a month, I think.
A little bit more.
Something like that. And he will be speaking on observing jet accretion flow black holes, or affectionately known as JAB for short. And he will talk about simulations that he's done in that, on that subject. So let us begin without further ado with Razieh.
Hi, can you hear me? Okay. It's always a great pleasure for me to talk here, and like what he said, I'm going to talk about a work that has been done very recently with Avi. Unfortunately, he is not here today, so I just kept him here with his picture. So it's actually about the yeah. So it's about the formation redshift of the massive black holes detected by LIGO. So we are all very much excited by the detection of the gravitational wave by LIGO. And as you see here is actually a movie showing how they're going to merge together the black holes. So I should actually say that LIGO did an amazing job of detecting different sources of gravitational wave very quickly. After about 2 years, we now have 11 detected sources with different mass distribution and different location. So it's actually very important to use this kind of information and shed some light about the source of the LIGO. So this is the whole purpose of this talk. I'm going to talk about the mass distribution and actually connect them back to the formation redshift or formation mechanism for these sources. So let's start with the mass distribution of the LIGO. So quite interestingly, about 70% of the LIGO events have mass above 20 solar mass. That was really surprising. Before LIGO, nobody expected to have such a massive object out there. However, as you know, theoretical people are very actually successful to find a lot of explanation for something that they see after observation. So this actually happens, and after about 70% of the events to be higher massive, people tried their best to actually explain it. So they actually asked themselves, what is the source for these high mass black holes and where they are located? So likewise, we also tried to ask ourselves a very simple question, but not necessarily very simple answer outward. So we actually asked ourselves, what is actually the source of these massive black holes above 20 solar mass? And actually, furthermore, we asked ourselves, is this possible that main sequence star would be a source for these massive black holes in LIGO? And if it's possible, then what is the redshift of the formation redshift for these progenitors? So these are two questions that I'm going to answer during this talk. So let's start with observation. So according to the observation and according to the most recent observation back in November, LIGO team has the different actually models for the redshift formation of the redshift detection of the binaries. So we are going to use the simplest possible case, which is the power law and almost constant, because all of them are allowed within the uncertainty in LIGO. So it's really good to be simple, at least for now, and leave the nature to decide which one is going to be real afterward. So we are going to, in this short study, we are going to actually consider the simple model, which is power law without any redshift actual evolution. And afterward, we tried our best to look for 70% of them that are beyond to actually belong to above 20 solar mass. So for that, we need to do some algebraic actually calculation, and then start with something that is about 70 gigayear parsec minus cube year inverse, which is the event rate density, and correct for these 70% of them that is above 20 solar mass, and then find about 1/3 of them that is actually according to this limit. So this is important because what I'm gonna to do is that I start with this high mass end, which is not really end because about 70% of them are actually above 20 solar mass. So I'm going to start with them, connect them back to the progenitor that we believe that it should be some kind of stars in the main sequence, as I will mention, and then see what is actually going to happen out there about the redshift formation and so forth. So in order to do that, we need one more piece, which is actually a map between the main sequence star that we believe that these are the progenitor of the black hole, and also the remnant mass. So it actually turns out that there are different maps that you could use, but most of them are just very complicated and there are a lot of things that are just uncertain. So it's really good to be simple and informative. So we used the result of a Nature paper just back in few years ago that is just very simple and very natural mapping between the main sequence star and remnant mass. So you see that here is actually different methodicities that we actually use, and for each of them, we can try to connect what we actually observe according to LIGO with their density that is actually in the progenitor. So if we do so, we can connect them here in this this is the map that I was talking about, black hole mass as a function of remnants, as a function of main sequence star, and then we could actually see the density of the solar mass that is actually going to be the progenitor. So as soon as we do this, now we have, on the one hand, we know what's going to happen. We start with LIGO, we went to the progenitor, but now we want to really compare it with what actually can be seen according to the real observation, according to the real star formation density that is actually in the universe. So here we actually integrate all the way all the star formation at different redshift. We also take into account that not all of the stars are going to end up with the binaries that coalesce within the age of the universe. So there is an efficiency factor here. And like what I told you, there is also the connection. There is a minimal mass that we should be beyond that in order to have remnant mass within the range that we are looking at. So different parameters are actually playing role here. So what we can do is that we just put all these curves on the curves that are actually coming from the observation. So this purple and actually blue line is coming from the LIGO. So for different parameters that we could consider the minimum mass for this progenitor and for different efficiency factors, we can put all of these curves up on the top of each other and be informative about the redshift formation. So if I want to tell you, for example, let's start with 0.1, which is about 10% of them is going to be responsible for the binaries that coalesce during the age of the universe. So it actually tells us that the redshift formation could be between 4 to 8. But you could be even less, actually, promising and just reduce it to 1% of the star to be the source of LIGO, then the redshift range is actually a little bit lower. So it actually starts from 2 and then go to the 6. So in any case, we see that there is a 1-to-1 map between the progenitor mass, actually the redshift formation of progenitor mass, different progenitor mass, and what you actually see in LIGO. And we can also try to see how much informative we are in the way that we can try for different parameters in the model that is actually, in our case, is metallicity. So if we increase the metallicity from 0.5% to 10%, we can see that there is just a little bit shift. It's not really too much. So this is the good news. We don't have too much dependency on the models that is going to give us something which is almost model independent. So we can also play around with the minimal mass. So if I want to remind you, minimal mass means that at different metallicity, there is a delay between, not really delay, but there is actually a percentage of the stars that after their death, they are going to lead us the black holes. So for different minimal mass, we see that the behavior actually changes. And again, the change is not too much. So these 2 plus is going to show us that we have a good room to be less model dependent. That is the good news. So we can do actually one more practice and also consider different values for percentage of the stars that are going to coalesce within the age of the universe. So here we see that if, for example, claim that 1% of these coalescing binaries are actually coming from the stars, then the redshift formation is actually a wide range, is from 0 to 8. If it's about 10%, it's 2 to 9. And if we really assume that it's 100%, that is not really realistic, then we see that, of course, it's going to be less informative. But in any case, we are less or about the reionization. That is important. So our point here is that we are less model dependent even after really carefully consider different models. And furthermore, we are going to be about or actually within the reionization of the universe. So to conclude, we have started with the LIGO events. We actually observed that about 70% of the LIGO events are associated with mass about 20 solar mass. So we try to find an explanation for them to be informative and simple enough. So we consider different models with different metallicities, and we actually search that for different metallicity. First of all, our result is not that much dependent on the metallicity. And second of all, changing the parameters of the model, that in our model is actually efficiency of a star to build up the binary black holes. If we start with 1%, the redshift formation is less than 8. Actually, if you actually imagine that 10% of these coalescing binaries are actually massive stars, is 2 to 9. And if you assume that is 100% of them are going to actually end up with coalescing binary, then you go from 4 to 14. So again, we have a good range for the redshift and less model dependent. So we are hoping to be informative. Hopefully, after a few more rounds of the LIGO, we can better see whether it's good to have redshift and not redshift actually evolving system or not, and better constraint on the actually parameters. So this brings me to the end of my talk. Thank you so much for your attention. Yes, please.
So I'm trying to understand what was the original assumption you made. So you assume a certain delay time distribution, and you assume no redshift of it?
Okay, good. So, yeah, I didn't have too much time to talk about this. Thank you so much for the nice question. So this is actually a very important question. Let me go back to this theoretical plot. So if I want to tell you what's going to happen, is that we start with stars in the main sequence, which is actually the horizontal line. And in the vertical line is actually remnant mass. So you see that according to different values of your parameters, which in this case is metallicity, it might be that not all of the stars actually, end up with a black hole. For example, if I start with very high metallicity, I'm not going to end up with 20 solar mass at all. But if I increase the metallicity, if I actually decrease the metallicity, the remnant mass increase, and I will be actually in the window of being 70% of them. So by delay, I mean actually this. I mean, not really delay, as I said, is actually some percentage of this star is going to end up with a black hole. So you really have to map them. Let's assume that you have a uniform distribution of a star, but according to the meteoricity or solar wind, that some of the mass is lost after all, and you don't end up with the same initial mass, then you have to take it into account. So what we did in our computations, we actually used this map, and we concentrated on two of them that could give us some signals that we are interested in, about 20 solar mass. So what we did is that we actually corrected for this mapping here. You see, it's actually, this is the connection from something that was observed in LIGO to the real density of the solar mass that is actually a main sequence star that are going to be progenitor for our detection. So this is the map that I was talking about. So I use different methodicities, right? And then for each of them, you have different maps. So this is one thing that we consider. So there is not any redshift evolution here. But about the actual data that we see according to the LIGO, there are different models that recent observation actually shows. One of them is just constant. One of them is going a little bit up in redshift. It's like a 1 plus z2 lambda. So in order to be simple in our map, we consider 1-to-1 map in redshift, which means that as soon as you are actually ending them, you don't get too much evolution afterward. So this is just the first simple computation that you could do, right? But you could have some delays and so forth, but there are a lot of uncertainties going on here that actually leads us to be less conclusive, right? So you could, I mean, if you want, you could just make it more complicated, but then there is not any chance of being informative. So I hope it's convincing now.
Yeah, no, I mean, ultimately you'll need to include all of these other possible variations.
Yeah, we will, yeah, but in order to be conclusive at the moment, we just try to be simple, but yeah.
Any other questions? If not, let's thank
Thank you.
Next speaker will be Dan
Hi, everyone. Okay, I took the title of Far Out Exoplanets. So, as you know, that's a frequent theme. But I really literally mean far away from this star, the host star. And by far away, this is a theory lunch. What I'm really talking about is further than you'd expect them to form, which would be maybe 100 AU. That's the scale of disks that we see around newborn stars. So if we find planets exterior to a couple hundred AU, then we have a problem on our hands. Did they really form in the disk? And if they didn't, how did they get there? Well, I'll give you two ideas about planet-planet scattering, which is the basis for how you can transport a planet born at about 10 AU out to hundreds of AU or even thousands. So planet-planet scattering is a pretty long history. Right after 51 PEG was found, theorists had ideas that two planets could scatter off each other, generating eccentric planets, and even producing hot Jupiters if tides cause the inner planet to shrink towards the star. So that gives you really close-in planets. But the theories also have a set of possibilities, logical outcomes to planets that are going unstable, pairs of planets or N planets around a star that start going unstable. So they could, of course, hit the star directly. They could escape. Those are kind of the two N members. The two planets could hit one another and merge. They could almost merge or mutually capture into a binary planet situation. And then two other ideas which haven't really been explored are that they could stop scattering. These are sibling planets around a given star, and a parent could come by and break up the fight. So that's what the first topic is on today. And then the second, another logical possibility is that they could just keep on scattering for the age of the star until we observe it today. And so I'm not much of a logician, but if you can find other logical outcomes for planet-planet scattering, maybe those are worth yet another paper. All right, so those are the two. The idea is to save things that are on their way to escaping, making them, breaking up the fight. That's the first project I'll tell you about. So a principle in this game is the comparison between the orbital speed and the surface escape speed. That is important from the surface of a planet. If the two planets are too puffy, they'll get close to one another and start hitting each other and merge before they have a chance to excite each other to a high enough velocity to escape. So you have to compare the escape speed from the surface of a planet to the orbital speed. And if the surface escape speed is high enough, that means the planets can whiz by each other, giving enough kick to cause them to escape from the star. So what one needs to evaluate to see these different outcomes is what's the smallest of the ejection timescale to escape from the star, the encounter timescale. This is an encounter of an external body, a parent, another star flying by, is what I'll tell you about, and then the age of the system. And those three, if whatever's most important timescale leads to ejection or saving, or just still scattering when you see the system. And something that I only barely appreciated when I started this was that the different masses of planets are the crucial outcome. It's not only the escape speed that matters, but it's the time scale, this T ejection. Because if another planet or even a test particle is scattering off a Jupiter-mass planet, then it takes only about 100 orbits for something to happen. Either the test particle hits the Jupiter or it ejects. So that's a pretty fast time scale. And so ejection can dominate if you have Jupiters. Whereas Earth mass planets, a 300th the mass of Jupiter, takes 1 million orbits or more. And you know that from near-Earth objects, which are moving around in the inner solar system for even 10 to the 7 years before merging with the planet or getting kicked to a different orbit. All right, so that is to say, planet-planet scattering calculations are mostly focused until now on Jupiter mass planets scattering off one another, and those are easier computations because they're faster, and they're more relevant to the observations because those are the planets we have in hand. But we're discovering smaller and smaller planets all the time, so this is now relevant. Okay, going again and again. All right, planets are common, especially small ones, and here's a plot that probably you've seen before, the planet size versus number, and it shows that planets smaller than Neptune, or smaller than about 15 Earth masses, are much, much more populous than gas giant planets. So most planet-planet scattering will be among these small planets. This idea about the parent breaking up the fight is not at all new. It was suggested for Sedna, and that's the inspiration. So this is work with a graduate student, Nora Bailey, at University of Chicago. And this is just an example system of 5 planets. It's planet-planet scattering in the context of a birth cluster, where we have stars flying by. So the density of stars starts off at 25 stars per cubic parsec, and that declines over the 10 to the 8 years as the cluster slowly puffs up and then evaporates. So the 3 panels show you the semi-major axis of 5 planets, all starting within 10 AU of the star. Their physical distance, so when they get kicked to a large orbit, they're going to periastron and then apastron, and the orbital eccentricities. And here is just the very first start of scattering up to 30,000 years. And once they start scattering, we send in the stars. So here's a star flying by just within 100 AU of the system, that first star that flies by just strips that planet. It got eccentric and then it got stripped. So that's not too interesting. But the second star that flies by, it comes to within about 600 AU of the system, and this orange planet, which is on an eccentric orbit at large semi-major axis, gets kicked and then interacts with that star, and its periastron gets lifted away from the scattering influence of the inner planets. So that saves that as on longer timescales, you can see that its semi-major axis just sticks there at almost, well, it's 500 AU about. So the upshot of this is that it's reasonably efficient to lift the periastron if a flyby occurs while a planet is hanging out at apastron, which it can do for millions of years. The mass determines how long it will scatter based on the T eject. So the Jupiter's inner Jupiter mass planets tend to scatter too hard, and they don't leave the planet hanging at apastron for very long. So only about less than 1% of systems of planets that would escape get saved from escaping by an external star flying by, if they're scattering off Jupiters. On the other hand, if Neptunes are scattering them, they can scatter them more gently. So the apastron of the planet that would be ejected, it's just slowly moving out, and it has enough time to wait for a star to fly by and causes periastron to lift away from the star. So it breaks up the fight, and then you can get, in systems of scattering Neptunes, you can get a little bit greater than 1%. About 1 to 2% of scattering systems will be left with one of these far-out exoplanets. So it turns out we were originally motivated by some direct imaging results of gas giants beyond a few hundred AU, but it seems like microlensing is the better tool for discovering these kinds of systems just because the masses are so low. It's unlikely to see Neptunes by their own infrared emission, but we can hope to search for planets through microlensing and correlate what look to be free-floating planets with stars that are nearby. Okay, so that's the first project, and the second project, I just wanted to see how much I could push this. So I wanted to put a bunch of Earths, 25 3-Earth mass planets, starting from 5 AU going out to 80 AU, just like populate the whole disk full of Earth mass planets, or populate the whole disk with Neptune mass planets, or Neptune mass planets plus 1 Jupiter mass planet just beyond the ice line. So the goal was a comparative study of different masses, throw in a bunch of planets and see what happens. Of course, the higher mass systems evolve quickest. This is 1 billion years on each of these axes. The previous one was just how it went unstable in the first 1 million years. So the idea is that over 1 billion year timescales, which is now kind of observable because those stars will be in the field, and the stars will be you'll have more stars at 1 billion years than you do at a 1 million year age. So it turns out that the system spreads kind of like an accretion disk. It started with planets here, and the interaction of the planets pushes most of the planets out. Some of them get kicked into the star. That's especially true in a bunch of Neptunes. So starting at 5 AU, 5 hit the star, 5 escape, and 6 survive and get pushed to larger semi-major axis. So this disk of planets is acting kind of like an accretion disk in the way it spreads. The other surprising thing was, this is the eccentricities, this is the inclination. I started with a disk with everybody within a few degrees, and the disk puffs up and becomes a donut. So we have a torus of planets with inclinations up to about 60 degrees. So what's kind of surprising is that you could have a relatively long-lasting, like gigayear timescale, puffy geometry, originating with a flat solar system, but spreading out to hundreds of AU and on a 40-degree typical inclination. So this donut geometry, if it's ever discovered, I'm not sure how you'd find all these planets around a single star, but if it's ever discovered with strongly crossing orbits at the moment of observation, that doesn't mean it didn't come from a disk. It could come from a disk. And so the upshot to detect these super Earths and Neptunes at hundreds of AU, we have to rely on microlensing. And so we have some of the first results from microlensing surveys showing really clear free-floating planets. On the other hand, we'll have a bunch more of these, of course, from W first. And the name of the game then is to see if they are still associated with their stars rather than being truly free-floating. All right, thank you. I'll take questions.
Any questions for Dan?
How do you distinguish between free-floating and planets that are associated with their stars other than sort of spatial proximity?
I think it's the spatial proximity. It has to be a statistical measurement of a correlation function between where you see a source star brightened by microlensing, and then with hopefully very good adaptive optics, perhaps with giant telescopes, spatially separate the stars that are hosts. Of course, the typical thing is to find a microlensing event towards the galactic center. Halfway to the galactic center is the lens, 4 kiloparsecs. And I'm talking about 400 AU. So we're a very small fraction of an arcsecond is what I'm proposing, where the host would be. And so what one would do is take your catalog of microlensing, free-floating planets and do an AO survey as close as you can get to those sources. Of course, after they've faded, way out, this is just a one-day thing, so already they're back to the baseline. And then look for companion stars. There's lots of stars that are in that little volume, but there should be a statistical enhancement due to these kinds of planets. Ramesh?
Sorry, I couldn't see your head.
Oh, I know. So the first part of your talk,
Yeah.
this passing by star kind of lifts the periastron.
Yes.
So by the time this planet is at apoastron, it's hardly moving, right? It's just
Yeah. Yeah.
So that means it doesn't matter whether the passing star is prograde or retrograde or perpendicular. It really doesn't matter.
Yeah, pretty much.
Pretty much.
Right.
You just need to give it some extra tangential velocity, give it some angular momentum, basically.
Exactly, yeah.
And that will increase. That's
Right.
really
So
nice.
then that outer planet could easily be going retrograde with respect to the original system,
Exactly.
if you could ever measure that.
Sure. So then the question is the 600 AU you just pulled out of the air. How often does that happen?
Oh, that was just a single integration. So what we did was several hundred experiments like that to see how often the saving effect happens. And then we put it in a particle in box type model of n sigma v of flux of intruding stars to work out this final percentage, which is about 1%.
I'm asking for the sun.
For the sun.
Yeah. How often would something come within 600 AU?
Oh, well, 600 AU in the field of the galaxy is about the closest we could expect any star to come within the age of the solar system. So we're the Brasser et al. Paper and Morbidelli and Levison, to explain Sedna, they appeal to the birth cluster of the solar system, where V is much, much smaller, so then the encounters can be gravitationally focused. Yeah.
So,
Hi, Maureen.
why is it that it's sort of isolated, strong scatterings that pump the eccentricity rather than sort of like cumulative, weak scattering with background stars?
Okay. Yeah, I'll repeat it. Question is, why is it a single star floating by that has this this effect of lifting the periastron rather than the cumulative torques of a bunch of stars floating by at larger distances? Is that a good paraphrase? So the answer is that as the planets are scattering off each other, they are pretty strongly coupled, and you need a comparable coupling of external perturbers to affect things. So you do rely on the relatively rare strong encounters.
And that kind of sets the periapse that you need for the encounter. Or the
Exactly.
scale. Yeah.
Yeah.
Okay. Thanks.
Another question about these great stars.
Yeah.
Would you expect these sort of events to occur more frequently in a cluster-like environment? And would this be a viable way of confirming the picture?
Okay, so the question is about whether it's a cluster environment I'm talking about. And yes, indeed, the model, the particle in box model of n sigma v, how often these encounters happen, relies on a cluster environment. Now, we are envisioning this sets up the system to have a far out planet, and then it can survive for the age of the star. So it could be observable in the field after the cluster dissolves. So is it more useful to look in the early days? Well, yes, because you could see further down the mass function of planets, because lower mass planets like Saturn's, for instance, would still be infrared bright, and they might be more easily detected. And so I'm arguing that it really, because the scattering thing down close to the star has to be low mass to make this ejection timescale long, the scattered thing also has to be low mass. And so the scattered thing, which you're going to see in infrared light, has to be below a Saturn or so. And so I think, yeah, infrared imaging of young clusters, even birth, like few mega-year timescale, that is still interesting, yeah. But mainly like Sphere and GPI, who are looking at of order 100 million year stars, they're going to miss this population. They have missed this population. Pretty much have done their surveys. Okay?
Now we move on to Amina Helmi. More information from the data release 2 of Gaia.
There you go.
Died. I think your power's up. Oh, it's okay. Oh, there it goes. Yes. Okay, great. Okay, can you hear me? Yes. No? Are you like this? Yeah, it's like this, it's okay? Yeah? Okay. So I'm going to be talking about some constraints on the distribution of mass that we've obtained from the Gaia data release 2. As you know, Gaia has been mapping the sky for a number of years now, and in April last year it produced the second data release that contains the motions of billions of stars in the galaxy, especially proper motion information, but also information on the line of sight of about 7 million stars. And if you have the motions of stars, then one of the things you can do is to try to establish what kind of forces are driving those motions, so you can map the force field in the galaxy. And ideally, that's what you want to do. And that's what we started doing with data release 2. So there are two bits to my talk. One is on using the motions of globular clusters around the Milky Way to try to obtain some new constraints on the distribution of mass at large radii. So within DR2, there was a science verification paper that I led on measuring the proper motions of the globular clusters that you see here in blue, 75, and the dwarf spheroidals, the classical dwarf spheroidals in red here indicated. And so for all of these objects, what we did is measure the mean motions to an incredible precision that was not possible before for such a large number of objects. And so if you actually have the motions you have measured the proper motions, and obtaining line of sight velocities for these objects is relatively trivial. It's not so many, so one can do this. Then we can actually integrate the orbits, and so that's one of the first things we did with having the velocities. What you see here are portions of the orbits, and this is already one of the first results from that we obtained from Gaia. So in blue you're seeing the globular clusters, which have more or less random orbits, as you can see. But you can see that the satellites of the Milky Way, even though they are not on a plane, right? So that's one of the other things that you immediately see. So not all of the satellites on this vast polar plane that has been talked about for quite a while. What you do see is some satellites kind of having motions like this, but some of them do define a structure that's relatively polar. But what you also see is that nearby dwarfs actually have very similar motions. Of course, LMC and SMC are a pair, but we also see Carina and Fornax here, Sculptor moving in the opposite sense, so we're really not seeing a coherent structure. And then over there, we're seeing another pair, which is Ursa Minor and Draco. And so I think all of this points to a certain degree of coherence that would be indicative of group info, as we see in, for example, lambda CTM simulations. But then what we did is we took the globular clusters, and because we have the phase space coordinates, we tried to model those, assuming that there was a distribution function using action angle variables. So using the action, so basically we have a distribution function of a disk and a halo, and what we're trying to constrain is in which gravitational potential are these clusters moving, such that we can reproduce the distribution that we see with its characteristic parameters. And so we had a model for the Milky Way where we actually varied basically two parameters. So this model has a disk, thin disk, thick disk, a bulge, and it has a halo. And we have two parameters for the halo. One is the mass, and the other one was the flattening. So what is the shape of that halo? And what we found, using a maximum likelihood and using the data from Gaia, is if you look at the mass, this is within 20 kiloparsecs, and the flattening of the halo, then what you see is, so this would be a mass that's relatively consistent with the mass that has been determined by other means. But what you see for the flattening of the halo is that indeed what you prefer is a halo that's prolate. So that's elongated in the direction perpendicular to the disk. And so it's very nice to see that the globular clusters are showing this, because also if we want to understand the motions, for example, of streams in the halo of our galaxy, like the Sagittarius stream, also seems to prefer a prolate shape. So that's so that's one of the first results we obtained. So the Q, the favored Q, is about 1.3 in this case. And the mass we obtained for the total mass, or the mass, say, within the virial radius, if you extrapolate, is 1.3 times 10 to the 12. This is consistent with what people are finding also doing other kinds of models for the modeling for the globular clusters and also for the dwarf galaxies around the Milky Way. So then this kind of proves the large scale, but also the Gaia data, the Gaia data release 2 has a 6-dimensional sample. So we have the 3D positions of all of the stars within a volume of something like 5 kpc around the sun. And we have the proper motions and the line of sight velocity, so we have the full phase space information for all of these stars. I showed this plot before. You can look at how the stars are moving, say, in the radial direction, in the Z direction, or in rotation around the galactic center. And if you look at that, then one of the things you notice is a lot of structure. So if you plotted the velocities of the stars, rotations versus radial direction, you actually see quite a bit of structure there. But you can also, one of the things you can also do if you're interested in mass distribution is take moments of the velocity field. So here are the different moments. So we're looking at mean velocities, mean radial velocities, mean tangential velocities, mean Z velocity. And you see patterns here. So the disk is not in equilibrium. You can also look at velocity dispersions. What we were interested in doing is to look at, again, the shape, but now nearer to the disk. So not in the realms of the halo, but now using this sample. And one of the ways to try to constrain the shape of the gravitational potential is to look at the cross term, so the tilt of the velocity ellipsoid. So if you describe the velocity distribution by a Gaussian, basically, what you have is you can describe the angle of that ellipsoid. So if it's aligned in RZ, so it would be cylindrically aligned, so you have a shape like this. If it's spherically aligned, then the shape is in the radial direction. And this tells you about the gravitational potential in which these stars are moving. And it's really independent on which population you're looking at. So these stars, halo stars, should all behave in the same way and be aligned according to the gravitational potential in which they move. So this is our measurement. So this is a plot showing, again, the Z direction, radial direction. So the sun is here at 8 and 0. And one of the things you see, and what's plotted here, are all these ellipsoids, the tilt, the angles of how these are aligned with respect to spherical. And the color coding indicates if you are redder, you're steeper than spherical. If you are blue, then you're shallower than spherical. Also, the shapes tells you this. So what you see is in the inner regions, you're more spherically aligned. But in the, say, beyond the sun or so, you're really rather flat. Your ellipsoid is very flat, this cylindrical alignment. So what does it tell you about the shape? But one of the things you can do is you can compare to what if the halo was spherical. If it's spherically aligned, then you get the black line here. And you see actually that in the inner regions, the shape is rather spherical. But as you go out, as you could see also from the plot, you get an ellipsoid that's very flat. So it doesn't align with radius. We fitted that. We looked at what happens by looking at different populations, so halos, thick disk, and thin disk, here in different colors. And you can see that it's always the same trend. In the inner parts, you get close to spherical alignment. In the outer parts, you get close to flat. So what does it mean for shape? So we have a very, so for dynamicists, a simple model, which is a model based on a Stackel potential. And the nice thing about the Stackel potential is that the ellipsoid is aligned with the coordinate system. So here you're seeing the different coordinates, and you're seeing this, that the Stackel potential that would reproduce the properties of the Milky Way would predict the ellipsoid to be aligned like the red curves. Whereas what we see is that it might well work in the inner regions, but in the outskirts, it really doesn't match the data. Right? So the shape, you would almost need to make it flatter as you go out in the galaxy. So the trends are wrong. And if you take another, one of the state-of-the-art models for the mass models for the Milky Way, that is this orange line, you also see it doesn't actually fit. So this uses a spherical NFW halo. And again, the trends are wrong. Actually, you see that in the inner regions, but you expect the spherical. Piffle doesn't give you that. And in the outskirts, the data is just shallower. So what have we done? We've actually measured these tilts, which vary from spherical alignment to cylindrical alignment, from the inner regions to the outer regions of the galaxy. And we really, what this is telling us is we really need to have new mass models that reproduce these trends. But what this shows in comparison to the models that exist already is that it's not going to be so trivial. Because you might not expect the central regions of the galaxy to be spherical and the outskirts to be cylindrical. You might expect that as you move out of the galaxy, you see it more spherical rather than more cylindrical. And I'll stop there.
Any questions? I see one way over there.
So you said that the halo is prolate.
Yes.
Now, wouldn't prolate naturally explain this? Because it should look more cylindrical, right?
Yeah, so that's what I thought too. We looked at the Piffle model, takes a spherical halo, but we looked at what if we vary the shape within that same model, and we don't get such a large variation. It doesn't actually match that. So the change in that orange line is very tiny for the prolate halo. So I don't really know how you get this.
It goes in the right direction.
It should go in the right direction, indeed. It should go in.
The prolate is even more than you think. It's this big, long rod.
Yeah, but it doesn't sound very right. Close to the disk, that the influence would make it so prolate. Maybe, I'm just wondering, because one of the things we're seeing is the perturbations are important, whether actually some of the shape that we're seeing is because of perturbations in say, the vertical direction.
Any other questions? If not, I have a short. How many stars have you noticed with escape velocities from the Milky Way?
Yeah, so I don't, this is a tricky one, because we are trying to measure what is the escape velocity of the Milky Way using the Gaia data set. And it turns out, yes, I mean, you could turn it around and say you try to fit the shape of the velocity tail and see where it goes down, and then say, okay, anything above that would be on the escape side. I don't really know the numbers, and there's not full agreement on what would be the escape velocity. Our estimates are a bit higher than what other people are finding, and we're trying to understand why this is the case. Yeah.
Thank our speaker again.
Yes, you need this.
Our next speaker is Anantua.
Oh wow, first time. All right. I'm Richard Anantua, a postdoc in Ramesh Narayan's group here, and I'm going to be presenting work I've been doing in collaboration with Roger Blanford, Sasha Shikovskoy, Elliot Quartert, and Sean Ressler on modeling emission in the inner regions of AGN using a methodology I call observing JAB simulations. And I decided that jets or outflows, accretion flows, and black holes interact together in observations and in simulations so that they deserve an acronym like JAB. And the methodology of observing JAB simulations allows us to parametrically explore variations on this theme. To summarize the observing JAB simulations pipeline, start with a general relativistic magnetohydrodynamic simulation of a JAB system, convert GRMHE variables like the rest mass density rho, the total gas energy density UG, the magnetic 4-vector synthesis GR, Vmu, and the 4 velocity into prescriptions for emission and also absorption, polarization, particle acceleration to emulate sources, adding an observer in post-processing to generate synthetic observations, which here will be images and spectra, to emulate, in this case, very long baseline interferometer observations. And we'll fix ideas by picking two Event Horizon Telescope sources, Razieh star at the Galactic Center and M87. Though, in general, we'll be having multi-wavelength observations that we can emulate using this approach. Onto our emission models. The first emission model I call simply the electron temperature model. And the basic idea is that in a two-temperature plasma, we could have the electron temperature and a roughly fixed proton temperature have a ratio that's dependent on this overall parameter constant F. And the plasma beta, which is the ratio of pressures of the gas component to the magnetic pressure component, in such a way that there's a critical value, beta C, such that the electron temperature is suppressed above beta C. And this is inspired by Howe's heating model. Another class of parametric models is the constant electron beta model, where beta E, not the total beta, but this time beta E, is fixed so that we can scale the electron gas energy density for relativistic electrons to constant parameter beta E and the magnetic pressure. We can also generalize this type of model to take advantage of the variation of the spatial variation of B by this magnetic bias model class of models, where we have the pressure due to the relativistic electron scaling as powers n of the magnetic field strength, where Kn is a constant for units in normalization. And we can also have other classes of models where we scale the emission function to the partial pressure P tilde of electrons emitting at the observed frequency to models that are based on parameters such as alpha for efficiency of momentum transport, shear or velocity shear, where z is the axial direction in the simulation and s is cylindrical radius. And you can also scale the P tilde to dissipation by current density J squared. And just to note, in our equal partition class of models, in our constant beta models, equal partition corresponds to having beta E of order 1. Now, we've fixed ideas with Razieh star, and the main observations that we'll try to emulate are related to the morphology, and we have EHT has a intrinsic size constraint of the emitting region at the galactic center, assuming a simple circular Gaussian emission profile of 37 microarc seconds, and this can be inferred by visibility over baseline variation, and having the full width half max give us a characteristic emitting region size here. We also have observations from the spectrum from 10 to the 10 hertz microwaves to 10 to the 20 hertz X-rays, and we note that there's a sub-millimeter bump in the infrared that we are going to try to emulate with our synthetic maps. Our first synthetic results are over our 230 gigahertz intensity maps over a scan of parameter space such that this F in the electron temperature models is 0.1 or 0.5, and the critical beta ranges from 0.01 to 0.1 to 1. And also, there's values of the bias model for n equals 0 all the way to n equals 4 in steps of 2. And electron beta ranges from 1 to 0.1 to 1. And for the electron temperature profiles, the characteristic images tend to be projections of a disk jet coronal region, and this region is predicted by geometry simulations to be the hottest given the form of the electron temperature prescriptions where we're heating up to a critical beta. And the parametric behavior is such that it tends from that thin photon ring plus coronal projection to a thin and asymmetric photon crescent at the higher values of F in beta caret. And for the equal partition inspired bias in beta models, going from n equals 4 to n equals 0 gives you a higher fraction of the emission concentrated in the outflow and also more asymmetry. And for the beta family, going to lower beta or more magnetic dominance in the plasma also tends to give you these thin asymmetric photon crescents that we saw in this parameter limit of the electron temperature models. So from two completely disparate parametric formulations, we can approach different parametric limits, and we can also have a completely different span of image morphologies, as we'll delve into a little bit later. We can also, given that observations prefer compact asymmetric emitting regions, we can do some ranking of our emitting region sizes and compare them with the Event Horizon Telescope size constraint by giving the images a characteristic size d, which is the diameter of the circle equal to the areas equal in area to all emitting regions with at least 20% of maximum intensity. So you might ask, why 20%? So if you have a dynamical range of 2 orders of magnitude in the EHT, 20% is roughly a geometric mean of this. But yeah, we can also do this for slightly different values. But as given, the size constraint is satisfied for the lowest n magnetic bias model. For an electron evolution model, which is using this simulation and solving the entropy equation numerically without putting any parametric models in it, so that would be the more computationally expensive but more rigorous computation of electron temperatures. We can also have a size constraint concordant with the highest F and beta C electron temperature model, with that critical value of beta being 1. And we can also have the lowest electron beta model give us all of these that are concordant with the size constraint are also roughly asymmetric crescent-shaped images, except for possibly the outflow-dominated image in the n equals 0 case. And producing synthetic spectra over the span of parameters gives us characteristic behavior over the two classes of models considered. So for the electron temperature models with these critical beta values, they all are roughly more peaked than the observational data, except for the highest F and beta C model, which was also one of our favored models in terms of the size constraint and morphology. And this model has a spectrum that over the 10 or so decades of frequency are somewhat concordant with the are somewhat concordant with the data. And these models we can conceive of as being emitted, or as having emitting regions that are dominated by some adiabatically expanding corona that has the temperature rapidly vary with radius. The equal partition inspired models tend to have flatter than observed spectra, and we can conceive of these as having some more outflow domination in the emission region, which can be conceived of as a Blanford-Konigal outflow. Onto briefly M87, we have a 43 gigahertz observation that gives us a characteristic profile of an outflow that we can conceive of as a pair of trousers morphology and a counterjet. And at higher frequencies, we'll see some shifting towards the core. And with our emission models, the magnetic bias model with the lowest exponent n gives us a broader collimation profile than the beta model. And it makes sense if you fix PE over B to the n, then the higher n should be more collimated given an emission, given in the simulation that the magnetic field strength is strongest in small cylindrical radii area. And these observational contours are given by VLBA and EHT. We can also note that in the intrinsic magnetic field substructure is that of kinking and swirling flux tubes here in this 15 gigahertz images, and we can emulate this with our lowest end bias model if we look at some kinking features that you may be able to make out in the movie here. So look at the magnetic substructure. We are able to explain with MHD instability some of the intrinsic or the inner magnetic field substructure. There's also some of our more complicated models where we scale the dissipation through P tilde to the current density, which is roughly the J component of the curl of B in the simulations. And we can replicate the same cadence of this observation where we see at 43 gigahertz this limb-Brighton structure with some flailing current sheets. And we see some similar flailing current sheets in this current density model if we look at these regions. And there's a somewhat of a marked difference in the spine, or there's strong emission coming from the center of this, which may be Doppler deprojected relative to this. But it's somewhat encouraging that we do have somewhat of a similar explanation for the limb brightening, or we at least have the presence of limb brightening in both of these. And there's also a prediction of bilateral asymmetry in our emission functions, where they all depend on the magnetic field through this effective magnetic field where BE is equal to Doppler factor (-1) times the co-moving magnetic field across the observer direction. So that should be different on two sides of the jet if we have a helical outflow. And our helical magnetic field in the outflow. So I'll leave you with my conclusions. Mm-hmm.
Do you have any analysis of what that would be like?
Yeah, so I did the transfer of polarization using some of these simulations, and the main thing that I'm looking for is in an outflow, for instance, in MED7, where we do have if we do have a synthetic polarization map with a large degree of linear polarization, that would give some credence to the picture of an ordered or helical magnetic field. That was a lot less time than I thought.
That was the reason that this time I tried to be less, other than that, the first time I was like 5 minutes and to be less than be more, but it was okay because you were the last speaker. So, there is no much reaction. That was interesting.
Oh, that's a very tricky question with the gravity results. So, Frank Eisenhower came here last week and he talked about the proper motions of these different hotspots, and they suggested that 20 or so degrees was the preferred orientation. By 20 degrees, I mean having the face